Morning, everyone. Hopefully, everyone is week's gone well. Um, where we left off last time, I'll try to just get us started. See if we can get out a little earlier today on a Friday. Um, where we left off last time was talking about the lithological plates, or the lithospheric plates, what is just commonly called plates in geology, and we were talking in particularly about plate boundaries. And where we left off was actually talking about divergent plate boundaries, where plates are being pulled apart. We talked about those being really important in the mid-oceanic ridges, but as we've talked about at the end of the class last time, there also are some divergent plate boundaries in continents, which are actually thought to be the precursor towards the formations of new oceans and actually pulling apart of continents to make new ocean basins. So the classic archetypal example of that is actually here in East African Rift, which is thought to be the birth of a new ocean. And eventually folks believe that this part of Africa will tear apart from the rest of Africa and a new ocean will be formed there. Similar processes are what actually created what we see and know as the Atlantic Ocean today, that broke apart the continents around the boundaries of the current plate systems and drifted apart over geological time. The other components we want to talk about, though, are those convergent plate boundaries. So we have three major types of convergent plate boundaries. Those are where you have oceanic plates going beneath continental plates. This is sort of the simplest to understand, if you will. Some great examples of this are the Andes Mountains. Others include the Cascade Mountains in northwestern United States. And this is a pretty simple case in the sense that the volcanic rocks from the ocean, particularly ones that have moved away from the mid-ocean rift and cooled down, they're more dense than continental rocks in general, and they get more and more dense as they cool. And as a result, plate tectonics sort of dictates that those oceanic plates will be pulled down beneath the continental plates and lead to usually what's called arc volcanics, or subduction arc, as people commonly call this. Again, the Andes being one of the best examples. The second form of a convergent plate boundary is where you have two oceanic plates interacting with each other. Same principles hold again. The more dense plate will have to will go down. What dictates the difference between which one's going to end up being more dense in these two oceanic plates, given they're both made of igneous rocks, is actually less to do with the composition of the igneous rocks and much more to do with the fact that which one is older, therefore cooler and denser, that allows that to go down. Often in oceanic settings, you'll actually see that one plate can start going down and kind of break off, and the other one will go down if more dense components interact, and those can lead to some major earthquakes as well as volcanism. But some of the best examples for the Fijis, at least one of the prettiest examples, certainly the Fijis, Samoan Islands. There are a lot of examples like this. Where is really the most complicated convergent boundary is continental-continental collision. In this scenario, the Himalayas is one of the best examples, of course. The Rockies nowadays are actually in a continental collision mode as well, but that's after a long episode of oceanic subduction sort of brought the continents in and led to continental collision. The key aspect of the continental collision is that you're actually having two opposing forces with relatively low density interacting with each other, and often it's actually really poorly understood as to understand what's actually happening there. And effectively, what folks accept is that things sort of just come in, the plates will sort of interact with each other and actually sort of delaminate and kind of melt, and often it's pretty unclear what's actually happening. The Himalayas, most folks accept that the Indian subcontinent is actually still going down below what's now currently Tibet, but how that exactly works is a major area of active research. So the convergent plate boundaries are particularly important for regulating things like climate, renewing the Earth's atmosphere, oceans, etc. One of the major aspects of how convergent boundaries play a key role in doing so is the fact that they actually regulate and carry massive volumes of sediments. So you might have seen images like I'm showing you here. This is actually from the Mississippi River Delta as it discharges in the Gulf of Mexico. But in all situations, as we're seeing igneous sedimentary and metamorphic rocks being weathered and eroded, both by physical weathering, ice freeze and thaw, aeolian wind dust, and also when you're seeing chemical weathering where things dissolve in water, those materials, sediments or detritus as sometimes we call them, are major fluxes of Earth's materials from land masses to the oceans. These are important for driving things like primary productivity, bringing the nutrients that sort of spawn life in the ocean settings, but also you know, our major mover of mass. And you know, go back to that sort of Neptunism versus Plutonism discussion we had on Wednesday. One of the key things here is that without the fact that convergent plate boundaries would carry these materials, take them down, and actually have them being placed in these arc environments, you would see that the oceans eventually would, of course, fill up. We know now that's not really the case, and that Neptunism didn't work in that way, and that's largely because convergent plate boundaries are responsible for recycling large volumes of the sediments in these environments. So, you know, for perspective, you multiply the rate of deposition by the number of years, you know, we would expect to see about 12 miles of sediments in the ocean bottoms. That's very, very clearly not the case. If you look at areas like Ohio that are deep sedimentary basins that have been brought onto continental land masses, we have about at most 1.5 kilometers between us and the basement of heavily metamorphosed rock. So you know, clearly the subduction at the oceans is a main driver of cycling things like carbon, water, et cetera, you know, into the mantle and out through volcanic settings. So the key thing here is what happens to those sediments. In reality, most of those sediments are broken down chemically, incorporated into magmatic melts, and are actually discharged to these arc volcanics. Some amount of them are, of course, just brought back into the mantle and recycled, which is, you know, important for rejuvenating the mantle as well. Not rejuvenating in any living sense, just in terms of moving those materials around. The next example, the sort of third major class of plate boundaries, of course, is transference faults. That's when things are moving past each other, not moving into or away from each other, just moving past each other. And transference faults, as I talked about briefly at the end of the last lecture, are common in certain aspects of the Mid-Atlantic, of all oceanic ridges. Certainly Mid-Atlantic, you see transforms where the ridge is actually offset a little bit. But the most classic example, or archetypal example of a transform fault, at least as we study in this country, is related to the San Andreas Fault. And that San Andreas Fault, you hear people talk about California falling off. Of course, it really won't, certainly not in our lifetimes. But California plate, or all of Baja California, is actually moving, you know, parallel and sliding past the North American plate. And that intersection, you know, just north of San Francisco is, or, you know, in the San Francisco area, really just north of there, is a major example of transform fault. One of the key things about transform faults is if you're thinking about plates sliding past each other, a lot of that movement tends to be very close to the surface of the Earth. So there's often scenarios where you see a lot of shallow ground shaking. They may not be as big a magnitude earthquakes, but often can do more damage. And as a result, these are just some examples from San Francisco earthquakes over time that you know, can be very large and at least do a lot of damage, maybe even disproportionately amount of damage as a result of the fact that they're relatively shallow in their existence. I don't want to in any way imply that divergent and convergent boundaries can't have earthquakes associated with them, but in reality, divergents very seldom do. They're usually mild and not really relevant to geological hazards. Well, and we'll talk more about earthquakes as we go on through the semester. Convergent boundaries can actually, particularly ocean continental convergent boundaries, but all of them in general can have major earthquakes associated with them. Of course, some of the sort of the Christmas Day or Boxing Day earthquake back in 2005 caused a major tsunami in Indonesia and Southeastern Asia, and many of the largest earthquakes in Chile and Alaska are all caused by these ocean continental subductions. The big difference there is those happen, you know, much deeper in the Earth's surface, and as a result, in many cases, don't do as much damage at the surface as transform faults. To give you a perspective on what these transform faults look like, this is actually not a road or a highway. This is a I can't draw very well. This is actually the transform fault in the San Andreas Fault here. So this is the basically Baja California. This is the North American plate, and these again are sliding past each other. And this sort of diagram, even though it's not always a transform fault, one of the best ways, and there can be many reasons why you see this, but one of the best ways to identify a fault when you're walking around in the field is actually to look for things like river and drainage systems and or lineaments like this. And this one happens to be, you know, a very well documented, easy to identify zone of the San Andreas. You'll note that there's a couple factors here. There's the fault, Okay, but you notice there's also this sort of topography around this area, and that's partly due to metamorphism, where these things interact with each other and sort of, sort of cause some friction and build up and sort of build up mass. But the other part is something called a pop-up, where the plates are in enough pressure that when they actually have at the end of the pressure to relieve the plates, when we relieve the pressure of those overbearing rocks, they often sort of pop up like along the boundary there. So that's what actually causes that topography you see in this slide. So obviously San Francisco Bay Area, if you will, is an area that's riddled by concerns and potential geological hazards related to transform faults. One of the more important ones is actually, it's not called the San Andreas, but it's a splay, or basically one of the areas where the transform fault, basically comes off of that major, the major San Andreas is the main fault system, but the Hayward fault is a splay or an offset of that fault. And that actually goes just on the east side of San Francisco Bay, and is been known to cause major earthquakes. Certainly, I think probably most of you are too young to remember the 1989 earthquake, but there can be some pretty devastating earthquakes that do a lot of damage. 1906 and 1989 are examples of ones that caused some major issues. This is actually from the 1989 earthquake along the Hayward Fault in this area. So to give you a sense, these can lead to catastrophic damage. Sometimes it's more continuous activity, and just sort of an eerie example is this. If you remember if you're a football fan, you remember the Cal Stanford football game in the Memorial Stadium at Berkeley. There actually is a transform fault that runs right through the stadium, and you can see that the stadium is actually, since it's been built, and I don't remember the year, has actually started to move past each other as the fault is slowly crept. So that building damage actually goes through the stadium, and it gives you a sense of the fact that these things are ongoing processes that can influence human life from a geological hazard perspective. One of the other things I want to cover in talking about plate tectonics is the fact that not all geology, not all of our geological hazards related to, earthquakes and volcanism, which we'll talk about in greater detail later in the semester, occur along these plate boundaries. The vast majority of seismic activity, of course, is how we determine where the plate boundaries are. Most of the volcanism is there as well, particularly in convergent and divergent plate boundaries, although there can be some volcanism tied to transform faults. But it's actually something that's a bit different. It's called hotspots or plumes. And basically, I want to I told you about the plate boundaries, but I want to tell you about the things that are sort of don't fit into that paradigm. And there are a number of locations on the Earth's surface where you see often some of the more intense episodes of volcanism, and these are called hotspots or plumes. And basically, these are areas where, if we go back to that concept of the Earth and think about the core, the mantle, and the crust, of course, we broke it down a little bit more discreetly earlier, on Wednesday. But there's a separate type of volcanism, which is driven by sort of gravitational instabilities at the core mantle boundary rather than the mantle lithosphere or mantle crust boundary. And those can generate really anomalously hot and anomalously large melts, which can basically ascend from the core mantle boundary and eventually impinge upon migrate through the mantle, impinge upon the Earth's crust, and eventually poke their head through. And these are what are termed the hotspots and plumes, and they can lead to major volcanism that is driven from much deeper in the Earth than what we see driven by plate tectonics. Their role in terms of driving plate tectonics is sort of controversial. Some folks believe that plumes actually are what eventually starts plate tectonics in an area. It's what causes rifts to occur in places like under the continents, in places like the East African Rift, or thought to be related to breaking up the Atlantic, which Iceland is a classic example of plume. Here, what we show you is a plume. Probably everyone knows what this image is, but it's in Yellowstone, right near Old Faithful. If you haven't been there, I definitely recommend you get there. But plumes are sort of the Wild West, if you will, or the part of the plan doesn't fit in that sort of neat idea of three types of plate boundaries. So the key thing here to remember is that these plumes actually are coming from the core mantle boundary and ascend over incredibly long periods of time, sometimes hundreds of millions of years. Most people think that the Yellowstone plume has been active for at least at least about 15 to 20 million years that we can document. Probably was active before that out in the ocean. So things like the Hawaiian volcanism was caused by a plume that's thought to be active for at least 45 to 50 million years, or even longer back, probably as much as 70 million years, I should say. And Iceland, for perspective, has plume interactions that have lasted for probably in excess of about 250 million years. So the key thing to think about here is that the same plate motions we've been talking about, where the continental and oceanic plates are moving on the Earth's surface, they will continue to move, but the location with respect to the center of the Earth of these plumes ascending and impinging upon the crust remain basically stationary. And as a result, you see a scenario where volcanism comes up from the core mantle boundary, and as plates move over them, you can sort of use the location of volcanism to track the relative plate motion. And a classic example of this, ties back to Yellowstone in the Pacific Northwestern part of the United States. What you can see here is that there are major episodes of volcanism where Yellowstone now is in the northwestern part of Yellowstone, Montana, and you can sort of track this plume hotspot back to an area called Mount Shasta and Crater Lake Caldera in New Mexico, and just east of Mount Shasta, I should say, in California, where you can see that the plume has remained stationary and the plates moved over it with time. So I got a question here about the Yellowstone supervolcano theory. We'll definitely talk about that in a bit more detail in the volcanics, but I'll provide a little commentary on it now. I think that, from a philosophical perspective, as a geologist thinking about who's, very interested in water, energy, climate, all the things that face modern society, from a philosophical perspective, the heat in the Earth's mantle that drives volcanism and plate tectonics is probably the greatest threat to most life on Earth. And I think that in reality, I don't know if the Yellowstone supervolcano is a supervolcano, or if it's gonna erupt at any time in our lifetimes. I probably suspect it wouldn't. But clearly, volcanism can irreparably and can catastrophically change the planet of the Earth really quickly. So the concept of volcanism being able to eradicate all of humanity, or all of even life on Earth is not impossible. In fact, supervolcanoes like Yellowstone are what are thought to be related to major episodes of mass extinctions that we talked about a little earlier in the past. To give you perspective on Yellowstone, you can, if you ever get the chance to drive from here west, I've done a lot as a geologist. There are locations you can go in Kansas where you can find, meters thick deposits of ash from Yellowstone-related explosive volcanism, that occurred in the last, few 100,000 years. So to say that Yellowstone can do a lot of damage and can potentially, lead to major changes on planet Earth and certainly the United States, it's absolutely true. Will it really wipe out Earth, or really wipe out our planet? I'm not sure. I believe that's irrelevant on a day-to-day time frame, but there is a lot of activity, and it's been increasing actually in Yellowstone. So stay tuned. But I think it's probably not too much to be concerned about in terms of survival. We got enough other things going on right now. But give you perspective, this relative plate motion is about an inch per year. That's about the average, 1 to 2 inches, about the rate of which the plates move, and it sort of track the long-term motion of the North American plate over the Yellowstone hotspot. So this is sort of tied into the question I got about the Yellowstone hotspot question, is that what we do know is that the magma reservoir beneath Yellowstone is getting bigger. Things are getting hotter. There's actually even been some reports in the last few years of some of the roads melting. To give you some perspective on how quickly things like this can change, I had a friend who works for the USGS who was doing gas sampling in the area, and they went out. This is quite a few years back. They went out to the Yellowstone location. They had a little boat. They rowed their boat across this lake. They did some sampling, and when they came back, their boat was out of water. And it's actually, it's over the course of a full day's work, but it gives you a sense of how much the area can sort of heave and haw, where literally the area they're in rose up and brought the water level for the boat sort of below that. So, for perspective, yes, Yellowstone's very dynamic and does represent a real threat, but probably not something you should worry about this weekend. Um, this hotspot of the Yellowstones where I've started are not entirely not entirely uncommon. Most of them, as you might suspect, are under oceanic plates, but that sort of makes sense when you consider the fact that oceanic plates cover about 70 to 75% of the Earth's surface. But you know, the other classic example of this is, of course, is the island of Hawaii. And actually, the island of Hawaii is a scenario of a exact same thing where the Pacific plate has moved over a constant source of volcanism from the coromandel boundary. And what you're seeing in the distribution of islands, in Hawaii, is actually the path of wander of where the plume head has reached the surface. So this will give you a perspective. Yeah, I'm sorry, it was about 78 million years ago where the Hawaiian plate was active, but this actually tracks from about 78 million years up until about 43 million years, and then the Hawaiian Ridge actually goes up to present-day volcanism. You'll note that you only see the islands of Hawaii on the map, and that's because although these other seamounts, or emperor seamounts as they're called, are still present, and in fact are at one point were actually islands above land surface, they've been eroded down by ocean wave currents and chemical and physical weathering over the years. So we can actually see the rest of this by mapping the occurrence of these things, but they're all below land surface now until Hawaii. And if you come back, you're lucky enough to live a million more years. If you come back, some of the older islands of Hawaii will be eroded and new ones will continue to form. But it's not an accident that the most active volcanic one is the biggest, because these things end up being really flat-topped sort of volcanoes that get flat tops in them. So they come up, they cool as islands, typically above land surface, and then the wave action of the oceans is only the top handful of hundreds of meters. And as a result, these seamounts can be volcanoes with perfectly flat tops, often with little carbonate islands where reefs and stuff like that are formed around them. They'll extend all the way back, and you can sort of track these down. So my big question here, this one I'm going to pause and wait for an answer, is that what happened 43 million years ago? Does anyone have a guess as to what happened, leading to this sudden change of direction in the Hawaiian and Emperor Seamount chain? I get awkward during long pauses as well. Maybe everyone's tuned out on a Friday afternoon, so I'll throw an idea out there. But the key thing to remember here is that, as best we know, the amount of wobble, or the amount of distance that the plume moves, is pretty minimal. And as a result, with respect to the center of the Earth, the plume can be conceived, or can be thought of as relatively constant, or in place. And actually, this bend in Hawaii represents relative motion of the Pacific plate. So we don't know why, but for from about nominally 80 million years to 43 million years ago, the plume was constant. The plate was moving south to north over the top of it, and then now, of course, since about 43 million years ago, the direction of the Pacific plate motion has changed, where the plate is basically slowly moving over it, allowing the newest volcanics to be over in this area. So this sort of comes back to the idea about the fact that we don't just have plates, that they're in motion. We talked about the fact that plate tectonics, of course, shape continents, dictate the location of mountain ranges, are relevant for water, ore deposits, and so many other things. But what really wasn't known until sort of the middle of, except in the middle of the last century, is the fact that not only were there plates, we could sort of get some sense of the activity around certain areas, and people as early as 1912, Alfred Wegener noted the fact that there's some common traits between these plates, that they had similar landforms, similar geology. But we didn't really have an idea about the fact that this is a dynamic system that moved around, that was sort of changing and evolving and recycling. So really, Wegener is credited for realizing that there's scenarios where North America and Europe and South America and Africa seem to have the same shape, and that obviously depended upon us having the capacity to have reliable maps. Remember, 1492, everyone still thought that when Columbus sailed the ocean blue, everyone still thought the Earth was flat, right? So we've come a long way in terms of actually drawing maps that can recognize the shapes of these things. But also, it wasn't just simple as that. There were certain fossils and rock forms that seemed to be on very different continents were actually or very different parts of the world now, but had very common traits in the geological past that we use to sort of tease this together. So, how did marsupials get from South America to Australia? How did similar species of snails exist in Scandinavia and northeastern United States? And why did the coal seams both correspond to locations in North and South America and Africa, and or why were they in areas where they're in the high northern part of the world, like northern Norway, where it's been it's largely too cold for sort of tropical remnants to be present. So really, this is where people started to take stock of this. The theory started coming around that maybe these plates are actually moving in some direction. That there was somehow plate motion that was the Earth's process of recycling. That was just like the idea of the age of the Earth. That was not a popular view for a very long time. It was quite vigorously fought against, and in fact, which a theory that's not entirely different to the ideas of how Native Americans got to the United States and how early indigenous populations moved around various continents, rather than actually accepting the idea or thinking about the fact that plates could move. Originally, people drew really complicated, extensive land bridges. So there were ideas going back to this where maybe it was actually island hopping between different places, and people could slowly move, and the fossils, not the fossils couldn't move, but the life forms where became fossils could move. Realistically, we know now that wasn't the case, and there are plenty of examples. One of the classic ones is Hipparion, which is a particular species of ancient horse, and it was found to live in France and Florida, at the same time, and people had that time drawn really complicated land bridges connecting North America and Europe, rather than recognizing that in fact the plates were just closer together at that time. So in moving forward, to give you a perspective on this, slowly from about 1912 until the present time, plate tectonics theory was accepted. But you might be surprised to recognize that, but as recently as 1950, 5 years after World War II, at one of the more prestigious geological conferences, more than half of the people, or about half the people, still embrace the idea of continental movement and plates. The early idea of plate tectonics, and the other half still thought that wasn't the case. It was land bridges or some more complicated thing. So, for perspective, it's only been 70 years since we had a majority of people starting to get behind the idea of plate tectonics, and actually, it's probably as recently as perhaps recently as probably the late 1960s, 1970s, before it was a well accepted theory. In fact, of course, I went to school learning about plate tectonics, but there are still faculty members in our unit that when they went to do their geoscience education, learned about alternative myo-geosynclinal theories and things like that. So one of the logical things we want you to think about or to know, is useful to sort of put together a understanding of how the science evolved, is how do we actually know that plate tectonics occurred? There are many lines of evidence. One of the main ones, which was actually the earliest sort of field of geoscience to evolve, was paleontology, and this is basically looking at fossils and fossil evidence around the world. In the case of the issue of plate tectonics, what people were doing were basically directly observing the same species of fossils on different continents in time correlated stratigraphic units. So looking at a rock unit that was 302 to 305 million years old, for example, in two different parts of the world on two different continents, they could realize the same index fossil, the same fossil that was diagnostic in sort of identifying time and space, and recognize they could be in different areas. And that often led to people sort of coming, sort of accepting the idea eventually. Okay, it's not possible for there to be a land bridge between all these different places and all these complexities of land bridges. That sometimes there were species that just made more sense than to be together. One of the things I'd like to point out to you here is that of course, if you're looking at the rock record, this we talked about this earlier in the semester about the fact that plants didn't radiate into continents until the Silurian, or basically about 400 million years ago nominally, maybe just a bit sooner than that, or more recent than that. But obviously, most of the fossils we'd be looking at, we can't really use marine fossils from the ocean. We have to use fossils that are available in sort of continental settings or near continental settings to get a better sense of this. So this is also one of the reasons I think this was fought against for a long time, is that there really wasn't evidence of land-based fossils or land-based organisms that became fossilized, in a lot of the rock record. So some of the other evidence for plate tectonics is actually tied to the location of glaciers and evidence of glaciers. So we don't actually see the glacier from a few hundred million years ago, but there are major evidence of major glaciation events, just like we see in Ohio, where the glaciers came down, caused a lot of erosion and things like that. Similar processes occurred in the northern and southern hemisphere in the past, based on where the land masses were at the times where we were last put together. That was in the Southern Ocean and nearly towards the Antarctic, and you can see that there was major evidence of glaciation in the southern Gondwanaland that had sort of all over the entire area, but didn't exist in other parts of the world. And the same idea was here. People try to put different, not necessarily land bridges, but just microclimates and things like that to cause this. But in essence, when everyone eventually started to accept the idea that everything was back together, people started to realize it was more likely related to glaciation. So, to give you a sense of this, there's some other factors that are sort of tied into this, but to give you a sense of this, most of the evidence that is in addition to that is actually related to the shape of the continents themselves and the fact that there's stratigraphically correlative, or basically the same rock formations on both sides of these newly established plate boundaries. And the key aspect of that, of course, is that it actually requires, in order for us to use that sort of last piece of evidence that the pieces fit together, we have to really go back to the last supercontinent event, which is called Pangea. So for perspective, the breakup of this supercontinent where all the plates were together probably started about 220 million years ago and really got kicking to about 200 million years ago. And that is the breakup that actually creates, for example, the Atlantic Ocean between North America and Europe and South America and Africa. Without that major event, we really wouldn't have seen the breakup of it's one of the major pieces of evidence, the fact that these continents fit together, that allowed people to sort of see visually that the concept together as mapping and things like that improved. So I'll come back to a video on this in a few moments, but give you a perspective. Starting 200 million years ago, we were together. By about 65 million years ago, you can see the continents were drifting in a scenario where this is at 135, and by 65 million years ago, you actually were spread apart enough that the Atlantic was fully developed at about 150 million years ago. And you can see that major things that set the way the plates are today, like India, is still sort of hanging off down here in the middle of the Indian Ocean, was actually probably related to volcanism that's similar to Hawaii, that started in Madagascar and eventually ended up being get going in India, that comes up and crashes into the Indian plate. So today, as things move along, by 65 million years, you start to see things look a little bit more like we do now. But really is been an evolution consistently and slowly over time from that last Pangea event that led to the scenario we see today. So I'm gonna go back here just briefly to this video. It does take a few minutes to play, but I think it's sort of a relatively interesting sense of just how this video will play. So perspective, this time frame at this point in time is back to started around 700 million years ago. This here is a trace of where the United States is. You'll notice that most of this is actually submerged underwater. There's not really a well-formed continent of North America. It's really what we call the craton. Some of the older proto-continents are put together. And also note that, by this point in time, I just missed the Cambrian Ordovician transition, but this is the first radiation of life. We see the major radiation of life. So note, Ohio, we're in the southern hemisphere. Most of this major land masses that are actually present, there was a Rodinia, a supercontinent that preceded Gondwana and Pangaea. And note that most of the land masses actually at the southern hemisphere, we, in North America and in Ohio, we're actually pretty close to the equator. And it's one of the main reasons why we see some of the first radiation of life was the fact that we are in an area warm enough to see oceanic life build it. Clearly, this is before the radiation of fossils of plants onto land, and before animals and larger, more complex life got going. So all the fossils you see here in Ohio are all these marine fossils, and we're in a perfect location here in Ohio at the time. This major landmass, just like those sediments I showed you coming down, would be depositing sediments out here in this ocean, and that's almost exactly at this point in time is where you see the Utica Shale Formation being deposited, which is major, thick, organic-rich rock that actually ended up being really important for oil and gas discoveries in Ohio. So I'll interrupt intermittently because the video is better than my talking, I'm sure, but just want to give you a perspective on what we see. One other thing, this is in Hawaii, but this gives you a sense of these little island arcs that actually form from mantle plumes, which are present and out there. I'm going to stop here really briefly. Notice, for those of you who feel like you've been trapped by COVID for far too long and want a vacation, notice you'd still be hanging out in the tropics here if you were in Ohio this time. But the other thing I want to point out is at this time, by the Silurian, Cambrian, in this Ordovician and Silurian, notice that there's a major accretion. Basically, this is what's now Scandinavia, England, Ireland, and all of northwestern Europe is basically directly in contact in originally an oceanic continental subduction, now then transitioning into a continental subduction that actually brought England, Ireland, and Scandinavia right up against North America here. I'm going to point out here also, you notice that Florida is still hanging out. It's not even part of our continent, hanging out in an ocean. Same for southern Texas, is still basically attached actually to what we now think of as South America. Eventually got accreted onto North America during one of these continental collisions. And when the Caribbean started to spread apart, Texas and southeastern United States actually stuck around with us. So just the perspective, seeing some of the continents, or some of the states rather, sort of get added on. For those of you from southeastern or northeastern, eastern Ohio, notice that the Florida, Carolinas, etc., are sort of coming on to the United States here, and this major mountain belt in between here is sort of the predecessor to the to what we call the Appalachians today. the Appalachians actually form over 3 successive continental collisions. The first of which was tied to the approach of North America. But this is really important for Ohio because at this point in time, you're actually depositing the organic matter that will become all the coal seams that drove the economy of Eastern Ohio for quite a long time. And actually, from an oil and gas perspective, at least, really important to thinking about Ohio geology is that you're actually burying what becomes the Marcellus Shale in this area, which is a major source of oil and gas for conventional oil development. So I'm not don't want to talk too much about oil and gas right now, but clearly here's Ohio, and the deposition of organic matter from that time led to the coal seams, led to the major oil deposits. And if you all didn't know, most of the oil industry started in Pennsylvania, but really got booming with Standard Oil here in Ohio. It's actually one of the key development aspects of Ohio's economy for quite some time. So it's kind of cool to think about here, the Permian. Right now we're sort of cooking along, excuse me, and life's teeming in the oceans. There's been great radiation of plants to the continents, and also mammalian, or not mammalian life, but reptilian life is still not there. Mammalian life's not there. But you're seeing radiation of life on the continents. But notice here that most of what is the United States today, you can see here's Florida, Texas, Nevada. The things that are missing at this point, excluding Alaska and Hawaii, obviously, are just the northwestern United States and California. They're not part of the equation yet. The other thing I wanted to call your attention to, I brought up this idea of the Appalachian Mountains. They're in full force here now as the 2 major landforms are pushing together here. And this is now the North American plate. Can anyone look at any geography buffs here who can see? Here's Florida. But what are the shapes of these countries? What does this look like to anyone? Can anyone tell? Yep, this is Africa. This is the Western Sahara, and actually, if you look at this, this basically shows that most of northern and northwestern Africa were Western Africa were basically attached to North America on both sides of the Appalachian Basin. And in fact, that's why oil and gas and coal discoveries in Africa are right along this area, Morocco down around to the Western Africa. So by this point in time, I'll just stop really briefly. We're at the end Permian, about 265 million years ago. This is where we've just come out of the major mass extinction. We've lost 95% of all life on Earth and almost all that life on land at this time. Here, by 220 million years ago, you'll notice, I want you to call attention to this now, Africa, South America, and North America are still close together, still breaking up that major landform. But watch what happens now. During this time, you're going to start to see these areas split, and this is where you see major volcanic emplacement along the eastern seaboard of the United States. And from here on out, you're going to start to see the plates diverge and North America and Africa split apart during the formation of the Atlantic. In case you missed it, that's the last time Ohio was in the tropics. So it stayed cold and gray from there on out. Actually, it's not that bad, but One last thing about the geology of the United States. Notice that by about 150 million years ago, we're starting to see what's called the Juan de Fuca plate crash into northwestern United States and southwestern Canada. Most of California has moved along this transform fault, and by this point in time, North America is largely formed. Most of the evolution is going to, from here on out, particularly from 70 million years in, is going to be in this region of the Rockies and the Basin Range, the Cascades part of the United States. At this point in time, you notice Alaska's docked. There's still no Hawaii, and we're right in the middle of the peak of the dinosaurs now. At this point, if you're a dinosaur lover, you're out of luck. The dinosaurs now been wiped out. And you'll notice you're starting to see the trace of Hawaii right here. So this will be the last time I'll stop to the end now, but at this point you're basically adrift. I think all of us could probably see most of the continents, at least identify them. Right now, what we call the subcontinent of India, coming at the south central Eurasia, is basically most of what dictates climate change and ocean evolution from here on out. It creates most of what the Earth looks like that we're dealing with today. So that's going to account for most of the rest of the what the planet looks like now. So key concepts: Earth's comprised of an inner core, outer core, mantle, and crust. The crust and upper mantle we call the lithosphere. This is where the plates are. These move along top of the rest of the Earth. And importantly, where the plates interact, that's where we find earthquakes, volcanoes, mountain ranges, major deposition of ore deposits, and are really integral for us sort of sustaining life and activities that humans involved with in the early days. So we'll come back to these plate tectonic boundaries a lot throughout the semester, but key things here to remember also: plates interact in different ways: divergent, pulling apart; convergent, coming together; and transform faults, moving past each other. So, and what we can say, and this is still a controversial aspect and a minor point for this class, is that we know plate tectonics are responsible for the distribution of continents over the last 200 million years, and certainly from that evolution, there are time constraints. We suspect it happened really well, really much the same way before that. Clearly, we have evidence to figure out where all the continents were and how they evolved. but we really don't know much about plate tectonics before that time frame, simply because we just have an absence of continental fossils and evidence that can go back. So just as another example, just like the early evolution of life, where there's only certain areas we can access that information. All right, I hope everyone has a great weekend. Everyone has until tomorrow evening for the problem set. Unless there's any questions, we're gonna call it a weekend. I hope everyone has a great weekend. I'll see you all on Monday.